Welcome, ladies and gentlemen, to C7-3 shells. And this could be, if I'm not mistaken, the last glue-in of textbook material. The last one. So maybe not a beautiful day for math, but maybe it is because it's nasty outside, raining, windy, but warm and toasty in here. C7-3 shells. So our final glue-in, and actually, if you flip back to our previous glue-in, these first two problems are actually exactly the same, but we're going to switch up whether we're using dx slices or dy slices. So we're really doing the same thing, but switching what type of slices we're doing. So the first problem is similar to what we did last time. So we have this region, and we're going to rotate it about the y-axis. So we'll start by graphing that. So let's see, it's about the y-axis. That means it's going to be symmetrical about the y-axis. So 3, and then goes up to 2. So we'll draw the original region. So there's the original region, and then it's reflected about the y-axis. So the symmetrical region, will be back there. And it's spun around, so we have, again, an upside down cone situation. And last time, we sliced perpendicular to the y-axis and had dy slices. So, and we did that, and they were discs. So this time, instead of doing dy slices, we're going to flip and do dx slices perpendicular to the x-axis. So I'm going to slice in the original region, so right there. So here is one of my slices. There's a dx slice, and that dx slice comes around and spins and creates a symmetrical slice over there, and then we have a cylindrical shell. So if you're kind of confused by that visual, go to Butenhoff Math and check out a link to a video that helps illustrate what's happening here. So stop this video immediately and go watch the video that illustrates this happening. So I'm going to pause. And welcome back. All right, so now you've seen that visual. So now you see we have a cylindrical shell type situation. So instead of a disc, instead of adding together a disc, we're going to add together the surface area of a cylinder. And if we add together all those surface area skins, those little cylindrical shells, that'll find the volume of this beast. So the surface area, and I should be more specific, the side surface area of a cylinder is 2 pi r h. So we need to somehow ground our problem. We need to connect our cylinder to the equation that we have, the original equation. So there's my cylinder. So okay, so I have my cylinder in here, and I'm going to pull it out, and then I'm going to try to connect that cylinder to the equation. So there's the original equation, x equals 3y over 2. And right here is where I have a coordinate x comma y. So there's a point on the curve. So I need to somehow connect my cylinder to the curve here. So I pulled the cylinder out, and there's the center, and I'm going to draw my radius to there, so it matches the fact that I'm connecting the cylinder to the curve right there. So I have this point xy. So let's see. Okay, so I need the radius. So the radius is this length right here. So from the center, from the y-axis to the curve, that's just the x-coordinate. So the radius is x. Okay, and then the height, because again I'm trying to fill in this formula. The height, okay, let's see. the top is 2, so this whole length is 2. Let's see, from the x-axis up, that right there, this distance here is x. This distance here is x. All of it's 2. This piece is x. All of it is 2. This piece is x. So the height of the cylinder, oh, excuse me, that's y. What the heck am I saying? So that height right there is y. So that little length right there from the x-axis up is y. The whole thing is 2. That piece is y. All of it is 2. So if I subtract away y from 2, that would leave the height. So 2 minus y. All of it's 2. Up to the point is y, so what's left over is 2 minus y. So then I can fill in my formula. So surface area, side surface area is 2 pi r. So let's see, r is x, and height is 2 minus y. All right, so there is a formula for the side surface area of our cylindrical shells. But we look at that and we see a variable of y and a variable of x. That's no good. We have 2 variables there. So one of those has to go. We'll notice we took dx slices. That means we want x's. So this y got to go. So let's see. Oh yeah, that's right. So if x is 3 over 3, y over 2, that means y is 2/3 x. We did that last time. So we just solve that for y, and then we substitute in. So surface area equals 2 pi x minus 2 minus x. What the heck am I doing? Y is more complicated than just x. Y is 2/3 x. So there's our formula for the side surface area of a cylindrical shell. So really, the hard part's over. So now I'm going to integrate, and I'm going to add together all of those cylindrical skins. 2 pi x, 2 minus 2/3 x, and then I have dx slices. So the question is, what am I integrating from what to what? So if you watch that visual again, you'll notice that we slice and it spins around to this region back here. So really, we only need to integrate from 0 to 3. dx slices, so I slice here close to the y-axis, that'll spin around. Right here, that'll spin around. So I integrate from 0 to 3. And using the calculator, if you do that, you should get 6 pi units cubed, which you'll also notice matches our answer from last time. Page 2. All right, so again, this is a repeat. So we have this, the same region. However, this time we're going to rotate it about the x-axis. So that means I need a symmetrical region down there in quadrant 4. So I'm going to draw the original region. So 3, 2. So there's the original region. And then that gets rotated about the x-axis. So -2. And we'll remember, it creates a cylindrical exterior. If we looked at the exterior of this thing, we would see a cylinder. But inside of that cylinder is a cone that's been bored out. So last time we sliced perpendicular to the x-axis and we got disc areas, we got disc slices, and that's what we did last time. So dx slice would give us discs. So that means if we do a dy slice this time, it's a cylindrical shell. It's 2 sides of the same coin. dx slices could be washers or discs. That means the other slice would be cylindrical shells, and they should get the same. We should get the same answer. So I'm gonna do a dy slice. So there's my dy thick slice. So dy, and that cuts and then spins around to the symmetrical region down there, and we get a cylinder. So we get a cylindrical shell, and then let's see, I have the point x, y, So I'm going to pull one of those cylindrical shells out. So there's one of the cylinders. And I'm going to be really conspicuous and say, okay, I need to find the radius, and I'm going to put the radius here on the right side of that cylinder, because right here, here's where the cylinder connects to the original curve. That's crucial. Look back here. Yeah, there's a radius here, but it doesn't connect to the curve. No good. We want the radius and the height to connect to the curve, the relationship, the mathematical relationship, x equals 3y over 2. So the radius, so let's see, the radius is the y value. That's easy. So the radius is the y value. And then the height of our cylinder, again, we need to fill in the formula. Surface area equals 2 pi r h. And so we got the radius, and then the height is this length right here. So that means the height is this length, which is x. That seems strangely easy. So the radius is y and the height is x. So let's fill in. Surface area is 2 pi, the radius is y, and the height of our cylinder is x. Okay, well, all right. Oh, so we're in a similar position. We have y and x. That's no good. So we need to get rid of one of the variables. So let's see, that's a dy slice. So that means I need to get rid of the x because I want y's. Oh, and then that's the original relationship. So surface area is 2 pi y, and x equals 3y over 2. There, the hard part's over, friends. So now, we're going to integrate from, let's say we're going to integrate 2 pi. Here's the formula for each cylindrical slice shell. So y, 3y over 2. And then we're doing dy slices. Okay, so let's see, we're doing dy slices, and arguably a hard part now is figuring out what to integrate from. So let's see, the original region we slice, okay, we're from 0 to 2. So we slice in the original region, and if we go back to that visual that's on my website, butenhoffmath.com, you'll see that slice would rotate around and would take care of the lower half down here. So we're all good. And we would use our calculator to integrate that, and your answer should be 8 pi units cubed, which of course matches our answer from last time. Page 3. All right, so here, now we have a bunch of curves, and we have to find a region, and that region's gonna be rotated. So I need to find out what we're even talking about. So we're gonna graph. So 1, 2, 3, 4, 5. So I have a couple curves to graph here. So y equals 2x, so goes up by 2. And then x equals 1 is the vertical line. And then y equals 0 is the vertical line there. So the region we're talking about is this little triangular region there. And then that is rotated about the line x equals 2. So this is different. So instead of rotating about an axis, we're going to rotate about a line here at x equals 2. So let's see, that's the line of symmetry. That means there's a symmetrical region back over here. Okay, and then, okay, so that's spun around. So it would have kind of a circular top, and then it's kind of like, it's a bundt cake, if you will. Kind of like a bundt cake. It's kind of like a volcano, if you will. So on the volcano, it looks like a volcano on the outside or something, and then it's hollow in the middle. And we're told to use cylindrical shells. So let's see. That means, let's see, if I did a dy slice, so if I slice like that, that would make a washer. So if I slice like that, I would have a washer. And we can kind of see a circular slice down there. So if I did that, but we need to do shells, which means I need to do the opposite of a dy slice. I need to do a dx slice. So I'm gonna go to my original region, and I'm gonna slice, and I'm gonna connect the slice to the original curve y equals 2x. I need to connect it to y equals 2x. So then I'm going to draw the symmetrical slice over here. And that means I have a cylindrical shell inside of there, which is hard to see. So I'm going to pull out that cylindrical shell. There it is. And again, I'm going to be very conspicuous about how I try to connect my cylinder to the original situation. So the formula is 2 pi RH. And now I need to quantify that, so somehow connect it to our relationship. So let's see. Okay, I have the height hanging out there. So the cylinder is connected to the curve, and I have points x, comma, y. So let's see, the height of the cylinder right there is the y coordinate. The height of the cylinder is the y value. And then the radius, I'm going to be very conspicuous here, and I'm going to connect back to the original curve. So I'm going to connect back to the original curve. So let's see, there's my radius. There's my radius. And I'm going to connect back to the original curve. So R equals, and let's see, let's see, what is R? So R is this distance here. And then, okay, so that distance from the the y-axis to the point would be x. So that distance is x. The full distance is 2. So if I subtract off that x, so the whole distance is 2, I subtract off that x, it's 2 minus x is the radius. So I've connected our cylindrical shell to the original equation. And so now I can start filling in what I know. So 2 pi r is 2 minus x, and the height is y. So, okay, let's see what I got here. I got a formula, so, but I need dx slices. I did a dx slice there, so I need to get rid of that y. So I need to substitute, so surface area equals 2 pi 2 minus x. And then the y value is, let's see, oh yeah, 2x. So now I've substituted in, and I have only x's there, which is great because I have dx slices, so now I can integrate. So from 0 to, oh, this is hard. Let's see, from 0 to 1 is the original region, and if I slice there, it would spin around and get to the right side there. So I'm going to integrate from 0 to 1. 2 pi 2 minus x. Hard part's over. There's the formula. And then I use the calculator, and I would get, what would I get? 8 over 3 pi units cubed. So typing that into FNInt and getting the volume there, it would be 8 over 3 pi units cubed. All right, you are now ready for the last textbook section, 7-3. Cheers.